Alright folks, Moonshine Radio here. Today we're going to talk about OFDM, and we're actually going to talk about an application of how we actually can use OFDM to transmit a text message. So let's get into that. Alright, here we got a text message. It will have 256 char. A char is simply a character like T, W for whiskey. You get it. Anyway, that will be limited to 256 characters. Each character will be 8 bits. So the total number of bits will be 2048. Alright, so that is our goal today on Moonshine Radio. Is how do we transmit 248 bits using OFDM? Well, here is a first draft of how we could maybe do that. This is looking at the spectrum, again, of what we would transmit. Again, with OFDM, we transmit all the bits at once, or you can. So we'll transmit 2048 sine waves at the same time. And basically, if the first bit or the bit was 1, we will make it have 0 degrees. And if the bit is 0, we will make it have 180 degrees. This is what's called BPSK. Now, we have to define it in terms of I and Q, and the way to do that is you put it into that e to the j term. So e to the 0 is 1, e to the pi, or 180, is -1. So basically we're going to make a vector of 1, -1, based upon whether the bit was a 1 or 0. Alright? Very simple stuff. Now, we've defined frequency. We can't transmit frequency, we have to transmit time. So how do we get this 248 vector of frequency bins into time domain samples? Well, we got to take the IFFT. And since we defined our bin 0 center, we first have to do the IFFT shift. Once we've done that, then we have to take the IFFT, and now x of 2 there is a time domain vector ready to be transmitted. Alright. Hopefully everyone's getting this clear as mud. Alright. So we got our 248 vector of time domain samples. We'll take the real of those vector and we'll make that into the I stream. We'll take the imaginary of the vector and that will be in the Q stream. Send that vectors to the IQ modulator at some RF carrier and amplify it, and out the antenna it goes. We transmitted our 2048 sine waves. Simple, right? That's basically OFDM in a nutshell. Now, here's where most people don't really talk about the receive side. So if the receiver were to just receive at that frequency and get 248 samples, do you really think it would be able to decode it? No. The receiver would basically say, what the fuck is this? And it would not decode it at all. So we really have to think about a better scheme to how to transmit this. And this might be a little bit better approach in our transmit spectrum, to have some zeros at the edges of the band and 0 at DC as well. So this is our proposed updated transmit spectrum. Alright? Now, we're not quite done there. We have to do some other stuff as well. So let's just take a minute to see our whole transmitted proposed timeline in time. I think we first should probably transmit a pulse. Why should we do that? That way the receiver knows where to start processing. So we will put a pulse here. The receiver can also use this pulse to remove the frequency offset, very key component. Now, the data, we can't just send the data. We have to send a reference before it can see the data. So we'll do a pilot block of all ones, and then we'll send the data block of 1, -1. This way the receiver can compare the pilot block to the data block to try to decode the bits. If we just send the data, the receiver would have nothing to compare it and would never decode it properly. So that's why we need the pilot block to give the receiver a reference. And very simple. Alright, so let's get a little bit more detail in our pilot block. Our pilot block is basically going to be all ones for A and all ones for B. Now, if we made all these have zero phase, that would be not very good because they would all constructively destruct and you have no signal. So one way to get around that is to make all the phases be random. And that's what we've shown here. So A will have a 1024 random phase vector with a 23 scaling, just a random number I picked. B will also be another random 1024 vector with a 23 scaling. And we shove it in our capital X of P here, and this is our pilot block vector. All still in frequency bins. Hopefully everyone's getting this madness. Alright, next we have to define our data block spectrum. And this is how I'll define that here. We'll have zeros, 0 at the center, some more zeros, and then we'll have a C vector and D vector. Now we have to relate these vectors to the pilot vector, and that's what I've done here. C is basically just A times C, and D is just B times A. So now our data here is referenced to the pilot block. And then we shove it in here in our vector. Again, this is still a frequency bin vector, and that's it. Now we have to get back to time. Well, how do we get back to time? Well, we got to take our IFFT here, as you can see. So again, you got the pulse, the pilot data block, and the data block. This is all time. So we got XPT and XDT, and this is how we get them back into time. We do the IFFT operations here, and all these frequency domain vectors are magically converted back into time thanks to the IFFT. So once we have these vectors now we're ready to transmit it. Now, one thing I should say is some people may take a little bit of that data and put it there, and a little bit of that data and put it there. They call it a fancy term like cyclic prefix, but that's just to kind of help multipath a bit. I didn't show that, but that's probably a good idea to do. Or you can just be lazy and repeat the pilot twice, repeat the data twice, or half of it, whatever you want to do. But the gist here is to try to show you need to have some type of preamble and some type of pilot and a data block, so the receiver has a chance in hell to actually decode. Alright. Now let's get some of the tasks that the receiver is going to have to do. Number one is going to have to first find the pulse so it knows when to start taking the FFT. Once it's found the pulse, it can use the data within the pulse to try to compute the frequency offset and then remove the frequency offset, so now both signals are at 0. Once these two steps have been done, we take the FFT of the data block section. Then we take the FFT, the FFT of the pilot block, then the FFT of the data block. Alright. Hopefully that's real clear. And finally we get back to our decoded bits by taking the angle of the ratio of the pilot FFT vector with the data FFT vector. And now we got our bits here. And since these are going to oscillate between 0 and pi or 0 and negative pi, we can just simply take the ABS. So now we have a vector of 0 and pi going back and forth, and we simply can say, well, if the individual bin is less than 90 degrees, it's a bit 1. And if the bin is greater than 90 degrees, it's a bit 0. Now we're back to bits, get the bits back into char, and decode the text. Well, that has been an overview today of how you can use OFDM to decode a message. For those of you that would like to see the MATLAB or Octave code of how all this was done, it's posted below this video. so you can steal it and say that you did it. Well, hopefully you're a little bit smarter today on how to really do OFDM. And again, all we're doing is transmitting a shit ton of sine waves at the same time so that you can get your data. Now, for those of you that think this has no application, I should say you probably watch this video because of OFDM. If you've ever used Wi-Fi, you're using OFDM. If you've ever used 4G or 5G, you're using OFDM. So hopefully you're getting my point here that it's basically used everywhere. So learn it. Moonshine Radio, folks. Thanks for watching.